In the last video, we designed this file, which is the neuron core, and we simulate and we analyze and synthesize. In this video, we're going to create a test bench file for this and try to simulate it on Model Sim. So now let us create a new Verilog file and let us save it as Testbench Neuron core and save it. So first we will declare our time scale like we did previously on the test bench. So time scale or 1 nanosecond and then 100 picosecond. And then we need to create our module. So module, and then we're gonna name it testbench neuron core. And then end module. What we need to do now is to declare our inputs that we're gonna simulate. Our inputs, so the input are reg, and then we have the test bench x1 and test bench x2. Those are axons, which they are of 3-bit. And then we have the snaps, which they are of 2-bit. It's testbench W1 and W2. And then we have our output, which is declared by the wire. And then the output is Y. And that we found it was Y. It was 3-bit. So 3-bit. And then now we need to insert our module, instantiate this one, the neuron core. So our module, this one, and then we can give it M1, module name. And then we have the testbench X1. So testbench X1. X2. And we have W1. W2. And then we have Y. So now we have instantiated our module that we want to simulate, the neuron core. And then now what we're going to do is to design the combinations of the input, all the input X1 and X2 and W1 and W2. But creating all the combinations, it will take a lot of memory. So we can simplify this by just create, for example, 10 random inputs of the axon and synapse, and then create corner cases for the inputs. So we're going to have a total of 4 corner cases and 10 inputs, random inputs. So let's create our initial begin. And then end. So what we're going to do now, it is create the random inputs. So what we need is for loop for this. And for example, e is equal to 0. It's 10 inputs of this. E plus 1. Begin. End. So what we need here, it is 10 random inputs. We're going to create these random inputs, for example, each every 100 nanoseconds. And then now we're going to create the random inputs of x1. So this is equal to a random so this one will create a random inputs of 3 bits, and then we're going to do the same for x2, and then we're going to do the same for w, for w1, but now this is 2-bit, so it will create 2 unsigned random bits. And then we have w2 and then this is of 2 bits too. And then what we're gonna do next is to create the corner cases, these inputs here, x1 to w2. So the first x1, so you can see this is out of the for loop. What we can do now, it is the x1, it is of 3 bits, so 3 bit, and then the first corner cases, we expect that maybe this one will generate a random number, so we need to make sure that if the all bits are on, we test for that too. So that is 7, and then we can do that for x2, all bits are on, and then we can do that for w1 when all the bits are on, so this is 2 bits, and then w2 it is 2 bit. So now here we have generated the first corner case. So this is one input, and then we want this to be delay of 100 nanosecond, and then we're going to create another corner cases, but this is when the all bits are off, so it's 0, 0, 0, to see if our neuron core behave in this scenario. And then we're going to create another corner case here too, and then this one is when all the bits are half on, half off, So for example, all the axons are on, but synapses are off. And then lastly, when half bit are on and half bit are off. So for example, this bit is off, and then for example, these two are off too, and here this one is off, and here this one is off. So just try to make different corner cases to see how it reacts. And then what we have done now, we need to test the function. So we need to create a test for all of this here to check if our output y is correct. What we can do now, we can create another initial begin. This one is for test. So this initial begin here, it was for creating random inputs and corner cases. Oh, this one must go inside here, because this initial begin, it is for generating the input combinations, and this one will be for the test. So we can create another for loop here. So we can say, for example, j is equal to 0, and then so we can see here how many times we're gonna test. We have created 10 inputs combinations plus 4. So let's say to be in the safe side, we are testing this 15 times. So if j is less than 15, and then j is equal to j plus 1, and then begin, end. So for example, now we need to test the output. For example, we can say what do we expect each time we generate the input combinations. So we can say expected out is equal to parenthesis. So our neuron core here, what it did, it was multiplying, and then addition, and then dividing. So we need to do the same here. So it is testbench x1 times testbench w1. So it was testbench x1, testbench w1. So this one here, we need to add with x2 w2, and then all of this here, it needs to be divided by 3. So we need to divide this like shift by 3. Is the same way as we did here. We divide it by 3 bit, and then we will look at the expected value. Let's declare our expected. So we can see that here our expected, it should be reg, and then we call it, we call it expected, and this is of the final answer. We found out why the total calculation, it is 6-bit, because here in our inputs, if we have the sum, which is 5-bit, and plus the carry, which is 1 bit, so it's 6-bit. So this one, in order to do this calculation, it should be also of 6 bits, because here in our divide, when we divide it, okay, this is 4 bit. So we need to change the def param also, def param here, of module 4 of m to be equal to 6, because the input here, what we are dividing, it is of 6 bits. So we need to make sure that we make that change too. Here we need to test. So what we can do now, it is first of all displaying the display all the axon and synapse. So x1 is equal to decimal, all the decimal that we have on x1, and then we have W21, and then it is all the decimal that we have provided, and then we have x2, W2, and then we have y, and then we have expected, so here we have all our, the first was Testbench x1, W1, x2, W2, and then it's y, and expected out. So now we have printed the inputs and our result in our neural model and what we expect. So let's capture it if there is any error. So if our result from the neuron core is not equal to expected out, so if it's not equal to the expected out, what we should do is to display to display the result. So you can say y out failed, expected is this value, and actual was, for example, this value. So the expected, it is expected out, and the actual that you have that was wrong, the neural core, it is ty. So this, it will run all the combination that we have generated here, and we know that each combination will take 100 nanosecond. So we need to give here a delay of 100 nanosecond, and then we don't want to capture the first zeros at the initial begin, so we need to do the initial begin too. So for example, we can write here and so at the start of simulation, x1 should be 0, same as x2 should be 0, and w1 should be 0, and w2 should be 0. And then our expected to, what we are testing, expected out should be 0 as well. This value here should be expected. So we need to declare the initials of the for loops, both for loops. So we have what we can call them is E and J, and those are their integer. So we have integer E and J, and then we need to define our simulation time. So, and then we can say just initial begin, and then here it is the final time that we will simulate, and the final time we know that we simulated, so it's 10 times 100 nanosecond, which is 1000 plus 400, 1400 nanosecond. So, and then the first 95 nanosecond, we don't want to capture anything, so we delay it. So this one should be outside of the for loop. We can say roughly our simulation time is 1500 nanosecond. So let us save this and try to analyze and synthesize to see if we have done everything correctly. So let us launch the module sim. Yeah, it's compiled correct. Let's compile our design. Compile the Neuron core and the Testbench file. Compile. Done. And then let's simulate the Testbench file. And add all the signal to the wave. Toggle leaf name and then simulate it in nanosecond. Run all. So simulate all up to 1500 nanosecond. So we can see all the generated random numbers. Okay, we see here that we have we don't have W1. Okay, so let's go back to the test bench and we need to change because this one is not X1, it's W1. Let's save it, go back and then recompile this and restart the simulation and run all again. No. Yeah, so we can see now we have W1 and this all of this from 0 to 6, all these 10 inputs here, 1, 2, they are random generated, and the last 4s here, those are the corner cases. So we have the corner cases 7 and 3 for the X, for W. So all of them are on, all of them are off, and half are on, half off. So, and then we can see here in the last result, for example, when it's 5, we can just test it because we don't have any fail on the model, so it's correct. So it is 7 times 3 is 21 plus 7 times 3 is 21. So that is 42 divided by 8. It is 5 point something, so we just take 5. So we can see that our neuron core behave correctly as how we have designed it here. So this one was for this video. In the next video, we will introduce a clock in our neuron core.